Well, we're at the last topic of the course, and my students have been sent to other sources for sort of a development and derivation of Stoke's theorem. So if you're a guest watcher, there's an assumption that you have a little bit of an idea of what is happening here. So again, we're looking at something related to a surface in space, and the concept is the line integral for work traced counterclockwise or right-hand rule orientation around a surface, but not a surface that's on a XY plane necessarily. It could be in space. And so through a number of other video segments, I've done some manipulating of other versions that were not Stoke's theorem. So I'm jumping right to what I would call as close to a formula as you could get for Stoke's theorem. You have to be provided a vector field. And in this case, we're looking at how the vector field sort of circulates around the surface. And then recall, as always, that z equals g of xy is the actual surface we're interested in. But we're not looking at the entire surface. We're just looking at part of the surface as it sits over or under the xy plane. So here's the given information. Our surface is going to be a paraboloid, or an upside down parabola bowl. And our vector field is given by components 4x, z, y, 4x, y. Remember, each of these components could be a function of x, y, and z. The author has names m, n, and p in the English alphabet notation for these. So one of the things I like about this problem, even if the physics is not something you are planning on studying, you've got a dot product here. The curl of the vector field involves both a cross product and partial derivatives. There's more partial derivatives here, and you're setting up a double integral of a three-dimensional surface. I mean, what else can you ask for? It pretty much has almost everything. It's like a whole bowl of Chex Mix. It's got everything in it. So let me just ease this up here a little bit. This parabola bowl, or paraboloid, as it is officially called, y-axis and x-axis. This is a circle. If you let z equal 0, you will find out it is a circle of radius 3. So that top view I am such a big fan of, or the view of our xy plane, is so critical here because it is a double integral. We're looking at a three-dimensional surface. It sits over, like this is like our floor, and then the surface would be the ceiling that's over the floor, radius 3. And so there's lots of ways we can write this, but I'm going to set it up dy dx later. I also need to calculate the curl of the vector field. And again, there are lots of notations for this. For my memory device, I like to go back to my old school linear algebra days. Okay, 4xz, that's the bottom row here. Y and 4xy. And then because I don't want to write very big and I just need a little memory device, these x, y, and z refer to partial derivatives I need to calculate. And this ends up becoming, the y derivative of that is 4x minus the z derivative of this is 0. The z derivative of that is 4x, And the x derivative of this is 4y. And remember, the middle term is negated or in opposite order. And finally, the x derivative of this is 0, and the y derivative of that is also 0. If that's not how you calculate curl, if you use your m, n, and p values, you'll get the same thing. So notice I don't have a z in here, so there's no z. That's a happy face. That means I don't need to worry about the double integral having variables that don't belong there. But if I needed a z, the surface is where I would get it from. I need partial derivatives. Look at that. I need negative with respect to x. So that would be negative g with respect to x would be the negative of negative 2x, which is 2x. And the negative derivative with respect to y is going to be positive 2y. So notice I'm in kind of math robot mode. I am plugging into a formula I don't need to understand. That's not a healthy way to survive long in the sciences. But like I said, a little bit of leeway because it's the end of the semester, and knowing that the theory behind Stoke's theorem is quite a bit more advanced than a lower division math course. So, dun dun dun. Let's set it up. Circle, radius 3, from negative 3 to positive 3, from negative square root 9 minus x squared to positive square root 9 minus x squared. Well, I probably could have said this earlier, but you know there's a pause button. You could have tried to fill it out before I did. I think by now we're starting to get close to that. You know when to pause me, don't you? Or at least mute me. The curl is 4x minus 4y, 0. Dot product, 2x, 2y, and then the z component is 1, designed intentionally for outward pointing, dy, dx. And because you guys have been here for a while and thought about this a lot with me, you know that sometimes I like to do this as well to just identify how these variables tie together and these numbers tie together. If I only ask you to set it up only, for my students' purposes, I would leave it here. But I could ask you to convert to polar. Or if it's simple enough, I could ask you to integrate it. And depending on the nature of the problem, if it's not simple enough, I could ask you to integrate it. But for setup only, I would leave it like this. It shows me that you know how to calculate curl. You would, of course, show me a method to calculate curl. You could use the curl formula, if not mine. You don't have to draw the 3D surface if I don't require it, but it's always a good idea to work on those skills. Top view, can't survive without it. Partial derivative information. And there you have it. See you later.